Over the past couple of weeks, my alum crystals have grown quite a bit. At this point, the tallest crystal that I have is about 0.8 centimeters in height, and the crystals appear to be pretty clear, and they cover about 40% of the inside edge of the vial. So there are a few factors that I believe contributed to the growth of my crystals. The first of which is that I placed my vial on a very sunny, well-lit surface on the windowsill of my dorm room, and this led to a lot of evaporation. So I believe that's a factor as to why the crystals grew so large and so fast. Another factor that I believe may affect the purity and the quality of my crystals is that there appears to be 3 white clumps of maybe mold or bacteria growing in the solution surrounding the crystals. And this could be due to a contaminant that fell in before the solution was sealed, or it may have actually happened after the solution was sealed if the solution was not sealed properly. But there's something growing in there, definitely a contaminant that may affect the crystal. So how much alum did we expect to create, and how much alum did we actually create? We can start by calculating the theoretical yield for this experiment. In part A, which is the first reaction involved in creating the alum, we know that we started with 1 gram of solid aluminum, which is 0.037 moles of aluminum. Then we added 50 milliliters of 4 molar potassium hydroxide, which can be calculated to be 0.2 moles of potassium hydroxide, which, because it's a strong base, dissociates completely and can be written as 0.2 moles of OH minus, and for now we can ignore the 0.2 moles of potassium. The aluminum is the limiting reagent, and so we can write the reaction as such. To get 0.03706 moles of AlOH4 minus. Then, part B involves the reaction of this amount of AlOH4 minus with 30 milliliters of 9 molar sulfuric acid. Here, we can calculate how many moles of sulfuric acid are inside of this amount of solution. We get 0.27 moles of sulfuric acid. When you react the two of them, you find that this is the limiting reagent, so these two have the same molar amount, and from this, we produce 0.03706 moles of AlOH3, as well as water and H2SO4 minus. In part C, the third reaction, we are reacting this amount of AlOH3 from part B with the remaining amount of sulfuric acid, which from up here, we know we have more than enough left to allow for a 3-to-1 ratio of sulfuric acid to AlOH3. Then we know that we produced 0.3706 moles of aluminum ions, as well as HSO4 minus and H2O. In part D, these aluminum ions are reacting with some of the potassium ions from up at the top here, as well as SO4 minus, to produce 0.03706 moles of alum, which is hydrated with 12 molecules of water. So the total molar mass of this molecule is 474.432 grams per mole. From there, we can calculate the expected amount of alum that we were hoping to achieve with this experiment. So here we have 0.03706 moles of alum, as we calculated up here, multiplied by the number of grams of alum per mole to get an expected 17.582 grams of alum as our theoretical yield. Our experimental yield was 13.53 grams of alum, so our experimental percent yield was 13.53 grams divided by 17.58 grams to get a 77%. Our percent yield was not 100%, and there are a couple of reasons this could be the case. One may be that during the fourth reaction while producing the alum, when we put the solution in the ice bath, we did not leave the solution in the ice bath long enough for it to precipitate all of the alum that we were expecting. And we'll have to check in next week and see where the crystals are at that point.